Welcome everybody to our joint Astronomical Kolloquium. My name is Stefan Jordan, and it's a great pleasure for me to introduce to you Bernedetta Ciardi from the Max Planck Institute for Astrophysics in Garching. Bernedetta Ciardi obtained her PhD in 2001 at the University of Florence. For the best PhD thesis, she was awarded with the Livio Grattan Award, the best PhD thesis in Italy. Afterwards, she had a postdoc position at the Max Planck Institute for Astrophysics in Garching, where she got the tenure track position in 2005. She got the Marie Curie Award of the European Commission, and since 2006 she's the project leader at the MPIA for LOFA. And she's in particularly interested in the formation of the first structures in the universe and the reionization of the universe. She investigated the effect of the radiation of the first stars on the interstellar clouds during the formation of the first galaxies. And today's talk is connected to these studies. We are looking forward to your talk on cosmic reionization, theoretical modeling, and challenging observations. We are looking forward to your talk.
Thank you very much. Okay, thanks for the introduction. You knew a lot of things about myself. And thanks also for inviting me here. It's a pleasure to be in Heidelberg. So what I'm going to talk about is cosmic reionization, both from a theoretical and also from an observational point of view. And in particular, we concentrate on observations of 21 centimeter line from neutral hydrogen, and what the instrument LOFA is trying to do in this respect. So just a very general outline for those of you who are not familiar with this field. So after the Big Bang, the universe is filled with hot plasma, and following its expansion, the last cools down and becomes neutral, and about working now? Yes. So about 350,000 years after the Big Bang, is this recombination epoch. Then after this, nothing particularly also interesting happens until the first structures and stars begin to form and emit ionizing radiation. This marks the beginning of the reionization process, which we believe to be complete by roughly about 6 or so. Then these primordial structures evolve into what we observe today. And from an observational point of view, we have information on the recombination epoch from cosmic microwave background, and we can, in the present generation of telescope, both ground-based and in space, especially in the UV optical and infrared, observe up to redshift of 10 or so. The latest record is a galaxy at redshift 111, which has just been detected recently by Pascal Oesch and collaborators. And there is still, though, this quite wide gap, which is presently not accessible to observations, but will hopefully be at least partially filled by the next generation of instruments, especially in far infrared and radio. So why do we say that intergalactic medium is ionized? Historically, this comes from observations of high-redshift quasar spectra, which show these very peculiar absorption features shortward of the Lyman alpha emission line, and which are due to neutral hydrogen intervening between the quasar and the observer. And if you look at the expression of the optical depth to neutral hydrogen, this is very high. So just a tiny fraction of neutral hydrogen would be able to completely absorb radiation. So the fact that we actually do observe some transmitted radiation means that the IGM is in a very high ionization state. So this is the reason why we talk about IGM ionization. So a set of constraints on observational constraints on reionization comes from observation of these high-ratio quasars. So this is a compilation of all the quasars known up to now with ratio above 6, which are, I think, 32. The latest, the one with the highest ratio, is 7.09, which was discovered in 2011 by Mark and collaborators. And as you can see, as you move towards higher ratios, you see more and more absorptions, meaning that there is more and more neutral hydrogen. So these sort of measurements can give you some information on the state of the intergalactic medium during the latest, the end of reionization. And as more and more galaxies and also gamma ray bursts are being detected at this very direction, mentioned in higher, the highest ratio gamma ray burst is at ratio 8.1, spectroscopically confirmed. These are used similarly to put constraints on the amount of neutral hydrogen in these fairly high ratios. Another important set of constraints come from anisotropies in the cosmic ray background radiation. So basically the photons of the CMB interacts with the electron as they're being produced during reionization. And from these, there are anisotropies that are created. And clearly, the largest the anisotropies that there are, the more electrons basically have been produced during reionization. So the extent of these anisotropies is typically described in terms of this Thomson scattering optical depth, which is an integral along the line of sight of the electrons. And so it gives basically an estimate of how many electrons are produced during reionization. But they don't tell anything on how they're distributed in time. So it's just an integral. So in principle, you can have all sorts of weird distributions. So this is a very recent figure showing how the measurements of the optical depth evolved through time from the early years of WMAP. Actually, WMAP1 is missing. It was an even higher value for the optical depth, down to the most recent number given by the Planck collaboration maybe just last month, which reached 0.055. So why, when the first values from WMAP came out, people started to worry because it looked like there weren't enough ionizing photons to ionize, produce ionization, so people started to think about all sorts of weird sources. If the number keeps going down with time, we might actually end up having the opposite problem, too many ionizing photons. So it's still not clear which direction this would go, but we're hoping that it sort of stays there, it doesn't keep going down. So these are basically the constraints that we have right now. So what is some constraint on the end, the latest stages of reionization, and how many electrons have been produced during reionization? But what we are completely missing at this point is some direct observation on the history of reionization. This we really don't know anything. And I'll come back to this point in a moment. So from a theoretical point of view, the ingredients that we need to model the process are the following. We did a model of galaxy formation, and people use their favorite approach using semi-analytic models, numerical simulations, or model hydrosimulation, or recently also these so-called semi-numeric approaches are becoming very popular because they try to take advantage of both semi-analytic and full numerical simulation approach. We need to know which are the properties of the sources of ionizing radiation. The most common one, and yes, people working in the field now sort of agree that they're also the main source of ionizing radiation, is for what concerns hydrogen, stellar-type sources, but in principle you can have also more energetic sources like quasars or X-ray binaries, and as I was mentioning before, also more exotic sources that started to become popular during the first years of the WMAP results, as I said earlier. So I don't want to go into many details, but I just want to give you a feeling for the sort of uncertainties that we are facing when doing this sort of modeling. And just a few comments on from the stellar type sources, we don't know much about the initial mass function in the spectrum of the early stars, which has started or driven the reionization process. And these properties can make quite an impact in terms of ionizing photon production, as you can see from the spectral energy distribution here. So the blue and the red line refer to the stellar population with the same salpeter EMF, but the blue line has a metallicity of 0.1 solar, and the black line is instead by metal-free stars. So in terms of ionizing photon production, this makes quite a difference. And also, if you just consider metal-free stars, but instead of the salpeter EMF, you consider more IMF more biased towards massive stars, in red, again, your ionizing photon production changes. Then we do know that the first generation of stars is metal-free, and then following metal enrichment, there is a transition towards a more standard star formation mode, so pop 2, pop 1 star formation mode. But first of all, it's still not clear which is this is the threshold when the transition happens, and even if we knew exactly that, we don't know very well how metal enrichment works. And so, again, this is a large uncertainty in the modeling, and by the way, this is something that clearly depends on time and space, so it's variable with time and space. And then there is the other big uncertainty, which is the percentage of ionizing photons produced by the stars, which are able to escape from the galaxy and into the intergalactic medium and be available for ionization. So this escape fraction, if you look in the literature, you can find both observationally and theoretically very different values, and sometimes really they range from basically 0 to almost 100%. So this is a very interesting problem in itself, but from the point of view of reionization, the only way that we can treat this is just to use it as a parameter. So this was just to give you an idea of how many, these are not the only ones, but some of the uncertainties that are associated with the properties of the high-redshift stellar type sources. And just a couple of words on the quasars. So there are evidences that the abundance quasars falls quite rapidly at high redshift. And at the same time, it looks like the full ionization of helium happens at a redshift 2 or 3, so earlier than hydrogen. So this requires a spectral softening towards high redshift, otherwise helium would become fully ionized earlier. So this seems to indicate that quasars do not contribute substantially to the production of ionizing photon, to the budget of ionizing photon at high redshift, but it could still be quite significant and important from the point of view of the energy input. So the last ingredient that is needed is a way to follow the evolution of the ionized regions. And also these can be done in a variety of ways, from the simple one, just counting how many photons and how many atoms you have, from much more complicated, fully 3D, multi-frequency, multi-species radiative transfer methods, and these are different approximations and approaches that you can find in the literature. So the usual approach that we use, or we use until now in our group to study reionization is the following. Both hydrogen and helium is the following. So to retrieve the properties of the galaxies and gas distribution, we use hydrosimulations, typically run with Garching, and we have a variety of simulations just to study the effect of box dimension, resolution, and others. And some of the results that I'll show now are just of this middle-sized box of 35 parsecs. For what concerns the properties of the ionizing radiation in this specific case that I'm going to show, we assume constant emissivity, varying redshift, and then we distribute it among the various galaxies present in the simulation. and we assume that the sources have a power level with a varying index, just to take into account the possibility of having a different source type, hardware or soft, or even a combination of the two. And propagation of ionizing photons is followed using a 3D radiative transfer code called CRASH, which is a multi-path approach to radiative transfer. It's continuously under development in our group. And in its present most advanced stage, it can follow the propagation of UV and X-ray photons in medium made of hydrogen, helium, and some metal species. But we usually don't switch everything on at the same time because it becomes too computationally expensive. So I just want to go into any detail. I just want to give you some points which I believe are important and sometimes are overlooked. So this is just the evolution of the volume average fraction of hydrogen 2, helium 2, and helium 3. And the lines refer to different models, source models that I mentioned earlier. So basically, as I was saying, the number of ionizing photons is always the same. What changes is just the distribution in frequency. And the cyan case is the one where only hydrogen is included, no helium. So here, the important point here is that the evolution of hydrogen, and this is an average case, but also if you look at the details, the conclusion is similar. So the evolution of hydrogen does not really depend much on the shape of the ionizing radiation and on the presence of helium. But on the other hand, the evolution of helium is heavily dependent on the spectral shape, just because you need more energetic photons to ionize it completely, which are not produced in high abundance by normal stereotyped sources. And a similar conclusion can be drawn from the point of view of the temperature. So these are just slices cut through simulation box, different redshift, and the columns refer to the different spectral shapes. So in these two cases, you have a component of high energetic photons, and so you reach temperatures which are typically higher than in a case in which you have only soft component of the spectrum. And if you do not include helium in your calculations, so this first column is the same as the second but without helium, again, the typical temperature is lower. So again, these are nothing particularly exciting or new, but it's often overlooked. So the point is that if you're just interested in following the realization of hydrogen, it doesn't really matter whether you include helium or not, or you calculate, or you properly model the spectrum of the sources. On the other hand, these components are very important if you want to correctly model the temperature of the IGN, and clearly also for helium, the spectral shape is very important. And I'll come back to this in a moment. So I think that what I show until now is that at this stage, so the theoretical modeling has improved a lot through the ages, through these 10 years or so. But there are still a lot of uncertainties, a lot of models which are included in these models, a lot of parameters, which are included in these models. So we really need additional information to be able to better constrain our modeling. And the ideal observations are really these one of the 21 centimeter line from neutral hydrogen, which has a ground state with a hyperfine structure. And simply because being a line, observation of different frequencies can give you information neutral hydrogen and different redshift. So in principle, you can really map the evolution of hydrogen in space of time. So it's really the ideal probe that one can have to follow the realization history. And typically the signal is described in terms of this differential brightness temperature between background radiation, which is typically the CMB, and the patch of neutral hydrogen with optical depth tau and spin temperature Ts, where the spin temperature regulates the population of the level. And this is the expression for the differential brightness temperature. So if the spin temperature is the same as the CMB temperature, this is 0, and so you observe nothing. If the spin temperature is below the CMB temperature, this is negative, and you observe the 21 centimeter line in absorption against the CMB, otherwise you observe emission. So the value of the spin temperature is critical for the observability of this line and the modeling of this line. And it is given by a weighted mean between the CMB temperature and the kinetic temperature of the gas. And so this is where, from a theoretical point of view, enters the importance of correctly calculating the temperature of the IGL. So these quantities here are the efficiency coefficient of Lyman alpha scattering and collision in coupling the spin temperature to the kinetic temperature of the gas. So in other words, if there is enough Lyman alpha scattering or there are enough collisions, the spin temperature gets decoupled from the CMB temperature and it gets coupled to the kinetic temperature of the gas, and you observe the line. You can observe the line. So the general picture that you expect is this one. The upper panel shows the evolution of temperature with redshift. In blue you have the CMB, in red you have the kinetic temperature of the gas, and in black you have the spin temperature. The lower panel shows the corresponding differential brightness temperature. So very high redshift, all the temperatures are the same, so the signal is 0. As you move towards lower redshift, the gas temperature goes below the CMB temperature. The medium is very dense, so collisions are efficient in keeping these two coupled, and you observe the line in absorption. Then below redshift 20 or so, in absence of other decoupling mechanism, the spin temperature gets coupled again to the CMB, and then you would observe nothing. But this is the range of redshift where the first source of radiation turn on, and in addition to emitting ionizing photons, they do emit also Lyman alpha photons. And Lyman alpha scattering is an efficient mechanism in, again, decoupling the spin temperature from the CMB temperature. So if you concentrate on this range of redshift and you include the effect of the scattering, then you see that, again, the spin temperature gets the kinetic temperature of the gas, and you expect to observe the line again in absorption. But through scattering, you can have also some heating of the gas. So if you include this, at a certain point, you have enough Lyman alpha background that heats up the gas above the CMB temperature, and then you enter a regime of emission. And this is actually where these sort of measurements are more powerful, because in this regime, the differential brightness temperature is directly proportional to the amount of neutral hydrogen that you have. So in this sense, it becomes a very, very powerful probe of the reionization process. So now, this sort of general argument is based on the simulated calculation, it's model dependent, so in reality you have fluctuations, some places you have emission, some places you have absorption, but it's just to give you the general idea of how things are expected to evolve with time. So what can we learn from this sort of observation? What are we aiming at measuring? So the holy grail of people working in the field is tomography, because in this case we have maps of differential brightness temperature at different redshift. So you can follow the reionization history, you can study the topology of reionization, and possibly you might also be able to learn something about the sources of ionization. This is something that the next generation of instrument is aiming at, like the SKA, for example, while the present generation, like LOFAR, papers, or NWA, try to measure fluctuations in the differential brightness temperature of the spectrum, so their aim is mainly to get statistical estimates of the process. Another possibility is if we will be able to detect a high-redshift very loud source. In this case, one could do the equivalent of the line of the forest and just detect absorption 21 centimeter along the line of sight and retrieve information again on temperature and amount of neutral hydrogen along the line of sight. And finally, people are starting to think about possibilities of cross-correlating the 21 centimeter signal with other type of observations. And the reason is mainly twofold. First of all, because so the signal that we are trying to detect is very, very small and affected by a lot of systematics. So cross-correlating two completely different observations might help in dealing with the systematics. And then this sort of cross-correlation would also be an external or an independent confirmation that the signal that you have detected is indeed the 21 centimeter signal. Because again, it's a very, very, very weak signal that we're trying to see. So among the various instruments that are presently trying to detect this signal is LOFAR, which stands for Low Frequency Array. It's an interferometer based mainly in the Netherlands, but there are contributions from several European countries, in particular Germany, which is just built 6 LOFAR stations. And each station is made up of a number of low-band antennas, which are active in the 20-80 megahertz range, and high-band antennas, which are sensitive in the 115 to 140 megahertz. And this is the range of frequencies which are more interesting from the point of view of the epoch of reionization, because here the contamination from foregrounds and noise are too high. So we're just using the high energy range. MBA is contributing as well with a LOFAR station. This is a picture. This is the high band field. This is the low band field. These are the hot fields that are surrounding our station. And this is the view from Google Map. Here it is Garching, where we have our installation party. So it's very conveniently located. So, what can LOFAR do in terms of the various action items that I mentioned earlier? Let's start with imaging. So, the LOFAR field is 5 by 5 degrees. So, to do this estimate, we have used 600 megaparsec box, which is a bit less, but almost managed to simulate almost the full field of view, using a semi-numeric approach developed by Andrea Mesiger, 21 centimeter fast. Again, I'm not going into the details, so if you're interested in we can talk about this later. I just want to give you an idea. So these are maps of differential brightness temperature. The A panel shows the purely theoretical estimate from using this code. This is convolved with a 20 arc minute smoothing for the Gaussian kernel to smoothing and sort of mimic the instrument. In C, we have added a noise corresponding to 600 hours of observation. Then, to have a mock data cube, you have to add foreground contamination and instrumental response, and then you have your simulated data cube, and then from here you extract the signal. So D shows the extracted signal. So basically D and B should be the same. Now they're not exactly the same, but there are some common features, and so I think the experiment test was performed to check how good the fit was, and the number in this case was something like 0.7, so it's not too bad. And this improves if you increase the observation time to 2,400 hours, which is shown in F. So basically, LOFAR is not designed to do imaging, and this is not going to be the main aim, but if enough hours would be collected in one single window, observational window, then maybe one could also try to attempt to do some preliminary imaging. And in the imaging category, you can also have regions ionized by hierarchical quasars. And the idea here, so this was something that this line of research was initiated by Tozzi and collaborators, and nothing much came out after that. But the idea is that one could use this sort of observation in combination with other observation quasars to try and improve our knowledge on high redshift energetic sources. And this is because, in principle, quasars should give a very distinctive imprint on the surrounding medium, but I'll come back to this point in a moment. So we are starting to look more deeply into this problem, and the approach is the same as the one that we used to run simulations of reionization. So we have Garching simulation to retrieve the source and gas distribution. The one that I'll show you is a 50 moving megaparsec box. We do have galaxies as sources, and also in the case that I'll show you now, we switch the quasar on at redshift 10 with sort of standard characteristics, although we have different branches changing the characteristics of the quasar. And again, the radiative transfer is followed by crash. And we have a variety of different models, switching on and off galaxies, on and off quasar, on and off X-ray contribution and others. Again, I'm not going into any details, I just want to show you one simple comparison between a case in which this is redshift 10, so this is a slice of the simulation box showing the fraction of H2. This is how it looks when you switch on the galaxies, and this is how it looks when you have also the quasar. So in terms of the fully ionized region, which is this sort of dark red region here, they look fairly similar, so the effect of the quasar is not so important. And these, you can also more quantitatively look at this if you check the distribution of the position of the eye front. This is for the galaxies and this is for the quasar, and the blue line is the one corresponding to the maps. So when you have only galaxies, the radius is about 12 moving megaparsec, while with a quasar the peak is at about 15. So there is a difference, but it's not massive. So the main difference, the main impact of the quasar is to produce this sort of ring of partial ionization, which is due to the soft X-ray photons, which are not present and not emitted by the galaxies. The problem is when you convolve this and you make your the expectations in terms of 21 centimeter observations, this is what you obtain. So this is a case in which the spin temperature is much larger than the CMT temperature, which we expect to be in this situation with this redshift. And this is what Lothar would observe in 2000 hours, the quasar and the galaxies. And you see that, yeah, the H2 region is slightly larger, but there are no real peculiar features that can tell you this is a quasar and these are galaxies. So this is just a signal to noise ratio that Lothar would be able to reach in the case of the quasar, this solid red line, and the galaxies, this solid blue line. So the point is that an instrument like Lothar should be able to detect these regions of hierarchy, and certainly they will be detected by SKA. But I don't think that this sort of observation would manage to tell us anything about the source of these large regions, because there are no obvious different features, at least in standard cases, most normal cases that we would expect to find.
Well, couldn't one just observe the AGN or the galaxy itself in the optical infrared?
Yes, I'm just thinking that in terms of 21 centimeter, absolutely, in that sense, definitely. But the point is that a lot of people were thinking that 21 centimeter measurements could be really used to tell something about the source of ionizing radiation, and alone, I don't think that this would happen, at least in standard cases. Obviously, the ideal way would be to detect some helium. In that sense, the signal would be completely different. So in that sense, yes, but just purely from hydrogen, it's a bit more complicated.
Bernedetta, sorry, can I also ask about your quasar?
Mm-hmm.
Still mass, did you see it? I guess you have...
So we have scaled the luminosity to basically match the one of the redshift 7 quasar, the model quasar, a redshift 10.
Okay.
And so it's proportional, basically. And the region that I showed is not an average region of the universe. It was simulated so that the highest, the halo with the largest mass halo was at the center of the box, and the mass of the halo is like 10 to the 10 solar masses, something like that.
There's no problems to detect the mortal quasar.
Low.
Yes, you would easily see it, the quasar.
Not necessarily, because I think that at that redshift there is already a lot of ionized region around the quasar, much more than at redshift 10. So that specific quasar it's in a already fairly ionized area, and we wouldn't detect much. So in terms of statistical measures, the statistic that I'll just mention is the variance, which is basically the average of the power spectrum. So also in this case we use the simulation that I mentioned earlier, 600 megaparsec box, and the variance from the simulation is a solid line here, which is fitted by this dotted line, which 2 parameters were used. This is basically let's call it duration of the reionization process, and this is sort of the peak. So similarly to what I've done before, you have your theoretical box, you have foregrounds, you have instrumental response, you have noise, and you have your smoothability. From here, you extract the signal. Once you have the signal, you calculate the variance and you estimate the best fitting parameters. So this is what you obtain. The blue line is the variance from the simulation, the dots are the mock data, and the red line is the best fit to the data. So it's not too bad. And even if you look at the probability distributions of the 2 parameters, again, the blue is the simulation and the red is the best fit. It's pretty good. And the estimate improves if instead of the variance you use the cross variance. So basically, the point is that the variance, to calculate the variance, you only use one frequency channel. But if you use 2 consequent frequency channels, basically the signal is the same, but the noise is uncorrelated. So in this case, the noise goes down, and in fact your estimates improve. And this is in terms of numbers that these are the blue numbers are the one again from the simulation. This is what Lothar would measure. So the nice thing is also these sort of numbers and errors have been obtained changing using different models of reionization. The estimate become worse if reionization happens earlier, just because there near foreground and more noise. But otherwise, it seems that Loeffler should be able to provide some statistical measure on ionization in a reasonable amount of certain time. Regarding the 21 centimeter forest, as I was saying, the idea is to have a radioloud source at high redshift and then to calculate, to detect absorption along the line of sight. Because this is the expression of the optical depth, so what you want is basically a clump of neutral, high density and cooled galaxy. So we have used simulations of ionization, as the one mentioned earlier, but at a much higher resolution because we want to resolve these small clumps. Once we have this history of ionization, we position source of a given characteristic given redshift, we calculate the absorption along the line of sight. So if you just concentrate on this panel here, the red line is the intrinsic spectrum that we will use. So we assume we position a quasar redshift 10 with a flux of 50 millijansky. And so these are characteristics of Cygnus A, so it's, it's fairly bright, but it was mainly for a comparison reason because previous works have used these numbers. The blue line is the theoretical absorption spectrum, and the black line is what Loeffler would observe with a bandwidth of 10 kilohertz and in 1,000 hours. So you see that you can clearly see absorption features. And this is true also at positioning the source at different redshifts. So Loeffler would be able to detect absorption features, but the problem is to find a high redshift very light source. And for the moment, so the highest redshift quasar is actually really white, and the highest redshift radioloud source is at 5.7. So we might not get lucky. So people were asking why not try with gamma ray burst, and actually the question is perfectly valid because after all we expect because gamma ray burst come from the death of massive stars, so we expect to have them up to very high redshift, they should be very luminous. They have been seen up to redshift 8 and something, so why not? So we have repeated the same exercise using gamma ray burst as sources. So first with the most optimistic case in which gamma ray burst comes from distribution of stars. So in this case, reasonable number for the flux is about 30 millijansky. This is what Loeffler would observe, and this is what SKA phase 1 would observe. So again, SKA would perfectly see all the absorption features, but even Loeffler.
So then one question, is the gamma ray burst observable for 1,000 hours? Because it fades, right?
Yeah, it does, but in the radio, because there is the time dilation, it stays there for long. Yeah. But that's not the main problem. The main problem is that if you go to more standard gamma ray burst, the flux goes down by a couple of orders of magnitude. So even if you consider full SKA, then the situation becomes much more complicated. So also this, unless we get very lucky or not, very viable sources, well, who knows, we have to stay positive. We might indeed get lucky. So the last point is cross-correlation, and what I'm going to mention here, although there have been studies of cross-correlation with CMB, with near-infrared background and others, I'm going to briefly talk about correlation with galaxy surveys, in particular Lyman-Alpha emitters. So the idea is that basically where you have galaxies, you produce ionizing photons, so you have lack of neutral hydrogen. So you expect some anti-correlation between the two signals. Lyman-Alpha emitters are more interesting from this point of view than Lyman-Great galaxies because they have additional redshift information, which is quite important. And in addition, there is an agreement between the Loeffler and the Subaru team to observe the same spatial sky. So we have focus on the studies with Lyman-Alpha emitters. For this, we have used 600 megaparsec simulations of reionization with full radiative transfer by Iliev and collaborators. And these were post-processed with a lemon alpha, approximate lemon alpha radiative transfer by Jensen and collaborators. So from these simulations, basically we have the distribution of neutral hydrogen and the 21 signal and the lemon alpha emitters. And we cross-correlate. So this is a 3D spherically average cross-power spectrum. In black, a redshift 7.3, and in red at 6.68, which are the two redshifts observed by Subaru, and then in green there is an intermediate value. So the main feature here is that the power, the intensity of the power spectrum goes down with redshift just because you have less neutral hydrogen. So this could be used as an indication of how much neutral hydrogen you have. More interesting though, in the lower panel you have the correlation coefficient, and basically you see that on large scale you have anti-correlation because it's where you have neutral hydrogen but not many galaxies, and as you move towards smaller scales the anti-correlation fades just because when you enter inside ionized region the hydrogen is ionized independently on how many galaxies you have. So this sort of flattening area here, scale, is, gives an indication of the typical dimension of the H2 region at that redshift. And in fact, as you move towards lower redshift, you see that the scale becomes larger because the dimension of the typical H2 region increases. So this is purely theoretical and in 3D. But first of all, Subaru observed only in a very narrow frequency range, so you're not in 3D, but you're in 2D. The delta Z is 0.1. So if you, instead of doing the 3D cross-power spectrum, you go in 2D, this is what you observe. You obtain a redshift 7.3 and a redshift 6.6. The solid line is average, and the dash, shaded area indicates a scatter from 10 different realizations. So the situation is not too bad either. You see that there is the decrement of the intensity of the redshift, and you can still see some anti-correlation, although the intensity of the anti-correlation now has decreased compared to the 3D case. But then there are other issues to take into account. So from the point of view of the 21 centimeter, you have to add the Loeffler noise. And from the point of view of Subaru, the field of view of Subaru is much smaller than the field of view of Loeffler. It's 1.7 square degrees at 7.3, and it's 7 square degrees at 7.6. So the number of galaxies observed by, which are expected to be observed by Subaru goes down. So it's about 20 at 7.3 and just about 1,000 at 6.6. So adding all these things together, these are the new curves that you obtain. So the solid curve is the average, and the dashed line just indicates what one would have without the Loeffler noise. So basically all these smaller scales here are completely illuminated by noise, and they cannot be used to retrieve any sort of information. Also from the point of view of the anti-correlation, it's still there, at least at 6.6 it should definitely be there, but at 7.3 the situation is much worse, just because you really don't have many galaxies. The situation improves a little bit with Loeffler, with SKA, just because its noise is much lower than the Loeffler noise. So basically the scales at which you can retrieve information, have information, extends to much smaller scales. So from this exercise, it looks like a cross-correlation between Loeffler and Subaru should be detectable, at least at redshift 6.6. And on scale, relatively large scales, larger than 60 million parts. Well, in SKA, we can have information also down to probably 20 or 30 common megaparsecs. I just want to spend the last few minutes of the talk showing you some very preliminary data from LOFR. So you might have seen these plots already because LOFR people have been showing it, but this kept being revised, so it's still preliminary. And actually, these plots that I'm showing are also not the latest one. In any case, so these are results or data from observations at the North Celestial Pole, which is the preferred window for LOFR in the high band range, as I mentioned earlier. So this first plot here, figure here, shows the data including the foreground, and these two are what the residuals that you have after foreground cleaning, with 114 and 169 hours of observations. And this is the upper limit to the root mean square that this data show. So the black lines refer to the data, and the red line to reference simulation result. So as I was saying, this is not the latest result, but the numbers don't change much. So the problem is that the results are still, the signal is still highly dominated by systematic effects, and not all of them are understood. So the guys doing the hard work are really working hard to understand the systematics. It's a continuous learning process, because it's a completely new instrument and observation, so they're really learning how to do this properly. And the main issue that they're having is the calibration. So it's very difficult to properly calibrate, but hopefully something will come out soon. So I'll leave you with my conclusions. So in terms of imaging, although this is not the main aim of LOFR, if enough hours are collected on a single field, we might be able to get some imaging also with this instrument, while from the point of view of statistical information, it looks like once these systematic effects are under control, this is something that can really be attained. In terms of 21 centimeter forest, this will be exciting to do, but as I was mentioning, the real problem is finding a high-resolution large source, while we'll try to cross-correlate the 21 centimeter signal with Subaru in the near future, and hopefully we can really detect something from there. And that's it. Thank you.
Thank you very much telling us what LOFR, SKA and other instruments can do to understand reionization in the early universe. I'm sure that there are questions.
I was wondering why it was not visible what the effects of quasar would be, because in the images that come directly from the simulation, it looked like a big effect,
Yes.
and then you convolve it, and then everything's gone.
No, the problem is that there is this ring of partial ionization, which means level of 10 to the minus 2, 10 to the minus 3, which is not enough to give a strong signal in 21 centimeter. So you don't really see the difference. The only chance that we will have is in the case in which the medium, the gas in which the quasar resides is cold. Because in that case, you would have this clear heating by the quasar, and that you would see the difference. But it's hard to imagine a case in which you're completely cold. and there is the quasar coming out. Usually the quasar are in high density regions, and so there might be some cases in which this could happen, but in the most reasonable condition, we don't expect to see it. Now there are some caveats and some some details that you could use, but in the most general and common case, it's not going to be straightforward.
Other questions?
Can you comment a little bit more on the word hopefully? You showed...
I'm not sure.
No, to be specific, I mean, there's clearly a large gap still between where the data hopefully will be. Is it clear what effects need to be worked through?
Okay, so there are 2 points. First of all, so the first thing that we want to show is an upper limit, okay? Because detection of the signal means that you really have to go down with the numbers, and this can be done, but it will require more observing time. From the point of view of the upper limit, so there have been, as I was saying, some issues with systematics. And at the beginning, for example, the sky model that was used to calibrate didn't have enough point sources taken into account. So the number of point sources was increased by a factor of 10, and the situation improved much more. But still, there were some weird effects that were not understood. So in the end, it was understood that that was because basically too many baselines were used, so that it was an overfitting that was introducing some effect. Then very far away radio sources that initially were thought to have no effect in the observation windows, it came out that instead there were some side lobes that were entering also from these very far away sources. So it's really, again, a learning process. And the team feels strongly about not showing results, just saying, okay, there are some systematics, but we haven't known what they are. So as long as they think they understand what it is, they're really trying to understand it properly so that they can then argument the result. And as I was talking to somebody before, basically the paper is there, everything is there, but just the final picture needs a figure, needs to be done. And it's nice because you can see also power spectra at different ratios, so it's very nice. But
An application.
And now they don't give, they don't say anything anymore about the timeline. They say be patient.
From Clark, we have learned a lot about galactic dust emission. So it's a fantastic mission for us who work on the galaxy. I was wondering how well you have in foreground contamination in this case.
So
in grid, how does this influence your results?
So the foreground is actually, so although we're talking about some order of magnitude more than the signal, it's true that typically they're very smooth. So even using, I think they used 4 or 5 different methods for foreground cleaning, the residuals are all consistent. So it's fairly robust. The ionosphere, it's something a bit more tricky. But also there, basically a percentage of, which is about 10-20% of the data, has been thrown away just because ionosphere contamination was too strong. But the other nights, it was, when it's fairly regular and quiet, it's not too bad. It's really, in the end, the main problem is just the vibration.
Other questions?
Data aside, how good is our theoretical understanding? I was wondering about the most relevant parameters for the prediction of 21 centimeter powers.
That's a good question. It's hard to tell, in the sense that there are a lot of parameters that are degenerate. Assuming that we are in the emission regime, so when the temperature of the IGM is already high enough that you don't care about these details, then it means that from a theoretical point of view, in principle, you can not care about the exact shape of the source of ionizing radiation, but just how many ionizing photons are there. How well we know that or can model that is another point, because again, escape fraction, property or efficiency of star formation, properties of the stars, it's really, it's very open. From that point of view, I think we need other sort of observation that will help us understanding better the properties of the sources. Maybe JWST will help a bit in this sense, but again, not completely, because this sort of observation we just observe the peak of the iceberg, so that they're not normal galaxies that we would observe. So they won't have normal properties. Most probably the population of galaxies using the bulk of the ionizing radiation are below the threshold, even for detection threshold, even for JWST. So, rely on maybe people keep improving on simulations of star formation and pinning down the properties of the sources. But I don't see how in the next really few years we can know this with some precision.
Other more questions?
Just another question to the foreground extraction. I'm wondering about how could it be that it works at all? To which extent you need to know something about the foreground sources, and are there some features that you focus on to extract it, or how is it done in general?
So the point is that the foreground contamination is, at least the foregrounds we know about, they're fairly smooth in frequency. They don't have features. Where you do expect features in frequency from the 21 centimeter signal. So basically this is the reasoning behind the foreground cleaning. And there are different methods that are used. For example, simple polynomial fitting, but this was shown that was not ideal because you can easily underfit or overfit, or with wavelet. I'm not a super expert in this. The wavelet method was working quite well. They were all based on basically on the assumption of the idea that and observations that foregrounds are smooth in frequency, while the 21 centimeter signal is not. So that's basically behind the cleaning.
More questions? If that's not the case, let's hope that both the observations and the theoretical models finally will tell us something about the reionization. If you have more questions, you can also join the after session in the Dorfschenke. Just come down and go with a few people to the Dorfschenke, and our discussions can happen. Thank you very much for your talk.